So this last example is an application of how we can use vectors in kind of a real world situation, which I think is actually really cool because when we think about like trajectories and we think about movement like your planes or your boats, we can see how using bearings and vectors can help us kind of break apart and learn more about the situation. So if we read through the problem, in this situation, we've got an airplane flying at a constant speed of 400 miles per hour at a bearing of north 70 degrees east. We'll talk about what a bearing is in a moment. A 60-mile-per-hour wind is blowing due north. What are the plane's actual speed and direction? Round the speed to the nearest tenth and the direction to the nearest degree. So direction is the same as what we were talking about before. It's the angle that the vector is going to make with a horizontal line, which we typically like to draw as, one of the x-axis in a little grid. And then what are we talking about with speed? So speed is something measurable about the vector. So in this case, the speed is actually the magnitude. Okay, so this speed is the magnitude that we're going to calculate. So hopefully you understand what's going on here. We have an airplane that's flying, but the airplane isn't flying just, with its own engine and nothing else is impacting it, right? There's a wind blowing at it. So the wind is affecting how fast the plane is going to go and also kind of affecting its direction, because maybe on your control panel you're saying I want to be going at a direction of 25 degrees, but a wind is blowing at me and pushing me down and I'm actually going at 22 degrees, right? So what we want to do is we want to figure out what's the combined effect of the plane's settings, right? Its own, like, I'm going at this speed and going at this direction, and the wind blowing at it. What's the actual speed and direction? So that's what we're looking for. So before we get into this, let's first talk about what is a bearing. So if hopefully you guys know your cardinal points, north, south, east, and west. So what we can do is draw kind of an XY axis, but instead of calling this X and Y, we'll make this our 4 cardinal points. You have your north, your south, your east, and your west. So when we talk about this bearing of north 70 degrees east, what it's saying is, hey, go north, and then I want to kind of fall down 70 degrees. So then my vector is actually going to be here. So let me use a different color. So I'll make my vector here in pink. So this vector shows north 70 degrees east. We went up north because the north came first. We're going to fall 70 degrees down toward the east, and this is my vector. So remember, direction needs to actually be with a horizontal, so we need to go on the west, east, west axis. So the true direction of this vector is not 70, but remember, these are all 90-degree angles. So when we're looking from east up to that pink vector, it's whatever the complement would be. So 90 minus 70 gives me 20. So the true direction of that vector for the plane is 20. Okay? And then we know the speed is 400 miles per hour. So again, this is your magnitude. So that just tells us the length of the vector. When we talk about what's measurable about the vector, that's 400. Okay? So this is my diagram representing the plane. Okay? Remember, the plane isn't acting only on its own. We have also got the wind. So if it helps, go ahead and sketch out the wind. So we can do the exact same thing. Make your cardinal points north, south, east, west. And we're going to draw a vector representing the wind, and I'll use this kind of yellowish orange for that. So the magnitude is once again 60 miles per hour. So that's the speed. So that's my magnitude. And it's blowing due north. So what's really nice about going due north, due south, due east, or due west is it means we're just going straight that direction. So we're going to start here and go straight north, 60 miles per hour. So that's the magnitude. So that vector just goes straight up. It doesn't have an actual degree, we're going to say, for the direction because it's not tilting. It's going straight. Okay? So there's my plane, there's my wind. And what we want to do is we want to figure out, okay, when I put these two together, what's the result? So this is the idea of the resultant vector. So what we're trying to do here, our goal, and that's a really messy thing. So let me rewrite that. So our goal is to find the resultant vector of the plane plus the wind. So we want this resultant vector. Remember, it's just a fancy way of saying let's add our two vectors. So in order to do that, we need to find the components. So that's really my step one. So once I understand the problem, and again, it's optional if you want to draw these diagrams. I think it's helpful for me anyway, so I can visualize it. But once we have this idea and we know our goal, my first step is now to find the components. So I'm going to write the components of each vector, right? And in order to do that for the plane, since this one does tilt off the north, right, axis, we want to create a triangle. So I'm going to do the plane here in pink. So what we're going to do is take out the right triangle from the diagram. So I know this direction is 20, this magnitude is 400, and what I want to do is I want to know its change in x, its change in y, basically your rise and your run, that idea. So we're going to go back down to our handy dandy SOHCAHTOA because it's a right triangle. So if I'm looking for x, we might realize, okay, well I have 400, which is the hypotenuse. X is the adjacent to 20, so let's go ahead and do cosine. So cosine of 20 equals x over 400. I can multiply both sides by 400 to get x equals, or I'll just write this more consistently, so 400 times cosine 20 equals x. And you'll see me leave it like this because remember, we want to round once at the end. If you do want to round now because your calculator can't do everything in kind of one step, remember, look at what we're rounding to at the end. We're rounding to the nearest tenth. So you'll want to round your intermediate answers. So those are not the final answers, right? The numbers you're using to get the final answer. You want to round it significantly farther than the nearest 10. So I might round it out to like 5 or 6 decimal places if I do want to round it right now. But my calculator can do everything in the exact format, so I'm going to leave it as 400 times cosine 20. Okay? So we want to do the same thing to find y. So y is my, so this was my adjacent, right? Y is my opposite. So opposite and hypotenuse, because I want to work with the number that I know, which is 400, which tells me let's do sine to find y. So sine of 20 equals y over 400. So 400 times sine 20 equals y. So the components of the plane are 400 cosine 20, comma 400 sine 20. So this is the plane. Okay, I'm going to do the wind here in this yellowish orange. So the wind is super easy because there's no triangle, right? If this is my wind, and it just goes straight up, 60, that means there's no change in x. So this change in x is 0. And y just goes straight up 60, so those components are super easy, 0, 60. So once we get the two separate vectors, remember our goal here is to find the resultant vector. So I'm just going to go ahead and add my two vectors. So remember, to calculate the resultant vector, all we're doing is adding the x's, adding the y's. So if this is my x1, y1, x2, y2, all I'm doing is x1 plus x2, comma, y1 plus y2. So then my resultant vector is 400 times cosine 20 plus 0, comma, 400 times sine 20 plus 60. And again, I'm leaving my exact values. So you'll see me just leave this as 400 times cosine 20, comma 400 times sine 20 plus 60, because I'm going to deal with all that at the end. Again, if you want to round right now, bump it out pretty far, so probably 5 or 6 decimal places, so it doesn't affect our final rounding, because at the end, all of our final answers should be the same. Okay? So this resultant vector shows us the actual vector of the plane as it's being affected by the wind. So what this is saying is now, we're going to look at the real vector, which represents the plane, right? The plane plus the wind, and calculate the actual speed, the actual direction, so the actual magnitude and the actual distance. All right. So if it helps, feel free to draw a diagram again. So remember, the vector tells us, the components of the vector tells us the change in x, the change in y, which leads us from the initial to the terminal point. So my magnitude, which I'm going to call m, is the hypotenuse, right? The direction, which I'm going to call d, is the angle it makes with the horizontal, with the change in x. Now, what are those x and y values? Well, that comes from our component form. So this x right here along the bottom is 400 times cosine 20, and the y, which is this vertical side, is this 400 times sine 20 plus 60. And now it's just a matter of going back to what we did at the beginning of vectors. Pythagorean theorem for magnitude, tangent, for direction. So I'm going to go ahead and work that out. So there you go, there's my work. And what I actually do is, because my calculator can do it all in one line, I do that first line and I take the square root of the answer. But if you're doing this in parts, you can see what I've done here is I put ellipses, these dot dot dots at the end, just to show it goes on for longer. And ideally you'd want to go, right, probably 5 or 6 decimal places, just so that final tenth doesn't get rounded too early. But regardless of what you did, check in your calculator, check your sequence. We should all be getting 424.3 miles per hour. So that's the true speed of the plane. It's not actually going what it was originally, the control, I guess the pilot would set, right? We want to go at 400 miles per hour, but it's actually going at 424.3 miles per hour. So it's going a little faster than the pilot had programmed. So then how do we find direction? Remember, we're doing tangents. So I'm going to do my work for the direction next. All right, so since we're solving for the angle, remember we want to do the inverse of tangent. And again, if you can't do that whole inverse tangent of 400 sine 20 plus 60 over 400 cosine 20 in kind of one go in your calculator, you can break it up and you can see how I've kind of bumped out my decimal places nice and far because we're rounding to the nearest degree, so the nearest one. So we should all be getting 28. So that wraps up this last example, this application of vectors.